Last term, we thought about delta H from the A-level perspective. It was a molar quantity. It was a state function, and as such we could apply the so-called Hess's law, because the state function says you start, you end, you don't care how you get there. Hess's law saying that delta H for a particular reaction is the same regardless of the path followed. So we applied this in the little equation. Delta H is where you sum up the heats of formation of products, sum up the heats of formation of the reactants, and subtract the sum of the reactants from the sum of the products. We applied this in a more elegant sense, where we combined equations to get an overall equation and combined delta H's in the same way to get the delta H for that overall equation. And of course the ultimate in that particular practice was the application of the idea to a Born-Haber cycle. We also estimated delta H by considering the endothermic bonds broken, the exothermic bonds made, and combine those two together. What we're going to do now is we're just going to continue on from that idea of delta H and look at a slight extension of one of our ideas, the idea that we applied lately, that delta H for a given reaction was a constant regardless of temperature. And after we've had that discussion, we're going to delve into much more general thermodynamic concepts and see how those apply to the heat of reaction, to that delta H of reaction. First of all though, we need to visit a concept that I hope is familiar to you from your GCSE and A-level, the idea of heat capacity. The heat capacity is the heat required to raise the temperature of a substance by 1 Kelvin. It is of course therefore measured in joules per Kelvin. The joules, the heat for every Kelvin that you raise the temperature. And the symbol for heat capacity is the rather sensible capital C for capacity. Chemistry, we don't often talk about heat capacity. We're much more interested in the specific heat capacity, which is the heat required to raise the temperature of 1 gram of a substance by 1 Kelvin. Okay, so now specifically talking about 1 gram. So therefore the units of that will be joules per Kelvin per gram. And of course the symbol for that then, the very sensible C for capacity, followed by the very sensible S for specific. Now as chemists, yes, we're interested in grams, but far more often we're interested in moles. So you might have encountered the molar heat capacity, which is the heat required to raise the temperature of, can you guess? 1 mole of a substance by 1 Kelvin. So of course that will be in joules for the heat per Kelvin, for the 1 Kelvin per mole. And that has the even more sensible unit, cm. Right, C for capacity, M for molar. Now molar heat capacity, we can see it for solids, and I'll give you a little list in a minute, and for liquids, but it's much more important that we think about molar heat capacities in the general sense of gases. And of course when you're dealing with gases you have to worry about not just temperature but the pressure and the volume. So we have the molar heat capacity at constant pressure, and the fancy word for constant pressure is isobaric. And that is, of course, the heat required to raise the temperature of 1 mole of a gas by 1 Kelvin at constant pressure. Same units because it's still a molar heat capacity, but now we use the tremendously unimaginative symbol Cp. And then, of course, we've got not just the constant pressure consideration, but also the constant volume consideration. Constant volume, the fancy word for that is isochoric. And so the molar heat capacity at constant volume is the heat required to raise the temperature of 1 mole of gas by 1 Kelvin at constant volume. Same units because it's still a molar heat capacity, but now the symbol Cv. Okay, so be familiar with these heat capacities as we go through. Before we move on to our discussion of delta H, it would be remiss of me not to dwell a little bit on heat capacities using this excellent table taken from page 616 of the book, in which the authors list some specific heat capacities, some molar heat capacities for a range of common substances. Now there's a historical aspect to what I'm about to discuss, and also a practical aspect for things that you will encounter later on in the physical chemistry part of your course. First thing is look at these entries, second, third and fourth. Iron, copper and gold. What you see is, at the face of it, no real relationship between their specific heats. Iron different from copper, very different from gold. However, if we multiply these specific heats by the molar masses to get the molar heat capacity, we get very, very similar numbers. Okay, in other words, at a very rough estimate, the specific heat and the molar mass are inversely proportional, because when you multiply them together, you get a constant. And this idea was used particularly by a chap called Cannizzaro in the 1820s and 1830s to get a measure of the molar mass of metals. A very important way in which early molar masses, particularly metals, was derived. Now, if we look at the next four, hydrogen, nitrogen, oxygen, and carbon monoxide, again we see a remarkable similarity between their molar heat capacities. Okay, and these, of course, are diatomic gases, and that is a general rule that there is a relationship between the fact that a gas is a diatomic one and its molar heat capacity, regardless of what the atoms are involved. Very, very similar molar heat capacity. And then as a last little trend, just look at some purely organic-y ones, methane, ethane, and benzene, and you can see that those increase along with increasing number of bonds that would have to be broken associated with the molecule. Not that heating them up breaks the bonds, but the more bonds there are to absorb that heat and vibrate and so on, well then the more heat you have to put in to increase up a mole. Okay, so some nice little trends associated with heat capacities. Next video, because I'm splitting into little videos now, we'll apply heat capacities to delta H to see how delta H changes with temperature.